Okay, yeah, let me begin by thanking the organizers for inviting me to give the talk here. Uh, so today I'll be going to talk about dynamics of information in collective states of a spin ensemble. So I'll go through some of the terms. The main part of like how we study the dynamics was something that was developed quite some time back. And in the talk, I'll try to start with some very introductory slides leading to that kind of a method before going into some interesting results. So yeah, for the expert, I apologize if this is a bit too elementary, but I've just kept it still for the flow of the talk. Okay, so let me begin. So the key word here, I assume, is collective states. By collective states, in my mind, I basically have collective of two-level systems. So this could be anything from rare earth spin ensembles. You can have an ensemble of nitrogen vacancy centers. You can have an ensemble of superconducting qubits, or even something a bit more natural, like say atoms in a BEC trapped inside a cavity, or molecules in a microcavity, a whole host of things. So for the purposes of my talk, I really want to focus on something that are called hybrid quantum systems, and collective states form an integral part of these hybrid quantum systems. So what are hybrid quantum systems? So in hybrid quantum systems, you really want to bring 2 or 3 different components together to get some kind of a synergy in the system, to get some kind of a cumulative advantage. For instance, you can think of superconducting qubits being ideal processes for doing processing. You have a static qubit in place, but you can have a memory element that comes from something else. So you can have an NV center placed there, or you can have another collection of emitters or two-level systems that could provide you with a stronger coherence time in lieu of the static qubit that is doing the processing for you. And all of these components can then be connected through a quantum bus that allows you to efficiently transfer information between all the different components. Right? So you can see you have 2 or 3 different elements, quantum systems, which have slightly different physical properties, slightly different descriptions, slightly different ways of numerically or computationally studying them, but you can bring them together to actually get an advantage in any quantum technological protocol that you're trying to implement. So the crux of the talk is trying to outline how information dynamics takes place across some of these components, right? So what are some of the advantages? As I mentioned, you can think of this in terms of quantum processing and storage. You can have a qubit, you can have an NV center, you can have a superconducting line resonator that's passing through. You can think for quantum communication, it's very popularly used in something known as transduction, where you want to convert photons from different energy regimes and then connect them to other parts of a quantum network for processing, right? So that is what is at heart at hybrid quantum systems. And this is this excellent review in PNS in 2015, which deals with a lot of different setups that you can bring together. So from the perspective of trying to study these systems, there is something that's it's really unique. So a certain part of this system could simply be a single qubit inside some kind of an oscillator. Think about how you would have harmonic oscillators or slightly unharmonic oscillators that you design in a superconducting circuit, and the dynamics can be exactly evaluated or studied because it's just a single 2-level system sitting inside some bosonic structure. Whereas if you're looking at something like a quantum memory, you have this huge ensemble of 2-level systems, and they are all, say, inside some other bosonic system or a cavity. Then the kind of analysis, the kind of studies that you have to do in both these extreme regimes become extremely difficult. So in the first case, you can, for instance, do exact calculations. You can calculate entanglement between 2 such qubits. You can calculate exact quantum dynamics. Whereas if you look at the second part, people talk about collective phenomena, and people often resort to semi-classical or mean field kind of calculations to solve these systems. right? Because of the dimension of the system. We'll highlight this point a little more clearly. So you can see there's a demarcation as to the kind of studies you can do for the two systems here, right? So let me start again from the very basic theoretical structure. If you just have a single two-level atom inside a cavity or interacting with light, you write down the age-old Jaynes-Cummings Hamiltonian. The Jaynes-Cummings Hamiltonian basically describes the interaction of a single atom with light. The first term is nothing but the energy of the atomic or the spin system or the two-level system. The second term here is nothing but the energy inside the cavity. And the critical component here is the coupling between the light and the matter out here. And this coupling is the one which is responsible for carrying information from one part to the other part. You can also have an external drive in the system, which coherently drives the cavity. And of course, you can have a whole set of other kind of interactions in the system. You can have counter-rotating terms. You can have optomechanical nonlinear interactions in the system. But the fundamental understanding would still just start with some kind of a Jaynes-Cummings-like Hamiltonian. You can extend this now to the picture where you have many, many two-level systems or spins inside a cavity. So it simply becomes the Tabis-Cummings Hamiltonian. But now, so now what I have is, instead of just a single two-level system, I have n two-level systems inside. I'm still assuming a single mode cavity. And then I have coupling between all these atoms. And in the most general case, I can assume that the transition frequencies of these atoms are not identical. They have some distribution. Again, the coupling between the atom and the light is not identical. They can have some kind of a distribution in the system, right? And then now in the context of dynamics of information, you really also want to take into account the different losses that come into the system. The simplest way to do it is write down the Lindblad-Master equation with a Markovian picture. So instead of working with the Hamiltonian, you can actually write down the Lindblad equation for the open dynamics of the system, right? So you can add some photon loss term here. You can also have losses to the spins that account for dephasing as well as spin decay and other kind of noises that you can think of, fine? So you can already see that the Hilbert space, the dimension of this is very, very large, because instead of solving for the pure state out here, I actually need to solve for the density matrix and the dynamics of the density matrix. And as n, the number of emitters increase, the Hilbert space dimension of this would actually blow up pretty quickly, right? So what are the standard ways in which people solve these systems? The simplest way is to write down some set of semi-classical equations. In semi-classical equations, you have these correlations, A dagger sigma I, which are the correlations between the atom and the light. You begin by simply factorizing them. So once you factorize these kind of correlations, you can write down a closed set of equations and then solve the dynamics of the thing. But you can see this is an extremely critical assumption that I'm making. In principle, I'm saying all kind of correlations that were there are actually being factored. So I can't use this to study quantum. Supposing I want to study quantum statistics of the light or entanglement being formed between light and matter, those things are thrown out of the window immediately. You can, of course, go to higher cumulants or take a higher order approximation to get back some of these correlations, right? So other methods that people use, you can use effective Hamiltonians, which only work for low excited states. You can use quantum trajectories if the ensembles are not that big, and if you can get away with solving the system using unitary dynamics instead of Lindblad dynamics. In some cases, if all your spins are identical to each other, you can also invoke permutational invariance and use the permutational symmetry to actually do a lot of the calculations. That gives you a huge gain in the dimension that you have to work with. But in general, looking for quantum solutions is in general difficult, right? So all has some kind of limitations. So one thing that we focused on at the beginning is trying to use a tensor network kind of a method. So variational renormalization group method that will allow you to go to, say, some around hundreds of spins and then use a time evolving block decimation kind of a solver to actually solve the dynamics of the system. Here you can do exact quantum dynamics, for certain, as long as the total correlations in the system are low, which is typical to how tensor network methods work. So this was developed we developed this quite some time back. I'll just go through the basic outline of what this method was for us. What we did was, if you have all the spins in an ensemble, you can think of it as a central body problem. So you can think of the cavity that lies at the center with all the spins around it. So all the spins do not actually interact with each other. So you can come up with a picture that's like this. And then you can divide it into different blocks. The cavity, which is the center, is not actually renormalized. The renormalization is done only on the space of the spins. Okay, so of course, this is a very superficial introduction to the topic. If you're interested in the method and how to implement it and you would want to know more, yeah, I'm happy to discuss that at some other point during the week. Yeah, so the idea is I can do some renormalization and effectively reduce the dimension of the entire system, but it would still allow me to do exact quantum dynamics and study how information is flowing, say, between a qubit and a large ensemble of emitters. Okay, so I can, once I've worked in the renormalized dimension, I can actually represent the entire master equation in the higher superorbital space, and I can write down something that looks similar to an effective Schrodinger equation and then try to solve the Schrodinger equation using the renormalization method. Okay, so that's the idea by which you can use a variational renormalization method to actually couple this exact solutions of a single system with exact solutions in a much, much larger system. Okay, so for the method part, I'll just stop at this point. All the theoretical and the numerical results that I'll show later, most of the exact quantum calculations were done using this approach. Fine, so at this point, let's just stop and let's try to look at some systems that we are interested in. So for the dynamics of information in collective systems, one of the key systems that we wanted to look at is what are known as atomic frequency combs. And atomic frequency combs are an interesting way in which you can try to look at the collective nature of many body systems and also look at the non-classical features that could lie in the system. Atomic frequency combs are quite popular in the study of what are known as multimode quantum memories. You can see this is just a theoretical illustration, but these were the famous papers by the groups of Nicola Giza, where they use these atomic frequency combs to actually store information that were carried through light pulses in this solid state ensembles. Yeah, so I think also Professor Malmer has some work on atomic frequency combs and related. So, okay, so the idea here is you can have a very short pulse that actually enters the ensemble. So if you think of the spin ensemble, it's connected to a cavity and you have a light pulse carrying some kind of an information that enters the system. You can have a very short pulse that enters, and then the atomic frequency combs absorbs the information, and it can, due to the constructive and destructive interference that goes on between, the light is actually revives at very, very specific points in time, right? So depending on the properties of the atomic frequency comb, there is a finite spacing at which the light would actually come out. And we want to use this to actually store information which are highly quantum, and we want to use our simulations to actually study that. Before this, we did a recent, in collaboration with the groups in IST Austria and TU Wien, we tried to create the superconducting, an atomic frequency comb in a superconducting system. So you can see, supposing if you have an ensemble out here, and if you have the usual vacuum Rabi oscillations, it's just a continuous thing. But if you can arrange them in the form of an frequency comb, then you have these sharp revivals that come. So if you have a homogeneous ensemble, you have Rabi oscillations. If you have an atomic frequency comb, you can have a periodic revival. And this was realized using a superconducting circuit architecture. It's a very, very small frequency comb. It was just 5 qubits that are trying to create this discrete frequency. So it's basically this structure, but with a single qubit in each space, you're trying to create that in a superconducting architecture, right? So you can see it has this frequency spacing that ranges from 30 to 50 megahertz, with transition frequencies of each around 5 gigahertz of the central frequency, okay? And then these are the results. These are the peaks that you get. Okay, so the first is you can see that the revival time for any information that goes in and it comes out, it's really a function of the spacing of the atomic frequency combs. So the spacing between two of the atoms or the qubits in the system. And then you can see that there is a very specific transmission spectra, and this transmission spectra is very consistent with what you would expect in an atomic frequency comb. And then here you can see that you have these sharp revivals in the output that comes, and it agrees very nicely with the theoretical predictions of the system. Okay, so for this, the theoretical prediction is very simple. It's just 5 qubits. You can exactly solve it using any quantum solver. But you can see, even for just using 5 qubits, you can arrange them in this particular pattern. And if you have any information that's flowing in, there'll be this nice revivals after specific periods, which is a function of how you've designed the frequency comb in the first place, right? Okay, so you can also see that the entire system is actually much more robust compared to a single qubit. It saturates at a much higher power than a single qubit would have done, at least by a factor of 6 dB. And then you can also repeat this entire experiment across a huge number of different photon numbers. So you can see you can repeat this entire thing even with an average photon number of 0.1, right? So even if you have some non-classical light that's going in, you can in principle just revive and get that out, okay? Fine, so this was an experimental demonstrations of how you can engineer this atomic frequency combs in the lab using superconducting circuits. You can do this with a whole lot of other systems. Okay, so let's get back to some theoretical and computational work. Now let's see if I have an atomic frequency comb which is, say, larger, say of 100 spins. So again, let me reiterate, my aim here is most of the analysis with higher number of spins typically tend to use some kind of semi-classical approximate methods. The question I'm asking myself is, can I use tensor network methods, and will that give me actually something that is better or something cooler can come out of it? So the question we're asking is, supposing I have an input state, which is, say, just a simple coherent state to begin with. At some later time, this time is defined by the atomic frequency comb. Can I get a state that is maybe close to the original state, but yeah, of course, due to losses and other properties, it's not really perfect. I want to make it as perfect as possible. And this state need not necessarily be a coherent classical state. It can be some arbitrary superposition of 1 and 2, 0, 1, or some Fock state or something. Or it can also be a cat state, right? So all I want is, I want this element to behave in such a way that if you put some random information in the hybrid system, say the left-hand side is coming from some other part of the quantum network, and it enters the frequency comb, can I get back this with a fidelity as high as possible, right? So these are some of the results that we had. So here I'm just analyzing the photon number. So analyzing the photon number is a very classical thing to do. It's not really looking at any quantum properties of the system. And here I can already see that for the coherent, arbitrary superposition and Schrodinger cat state, the photon number actually revives quite well. If I look at the Wigner function, I can see that there's a parity inversion at the first revival, whereas at the second revival, the parity comes back. You can see that for the cat state, the parity is preserved throughout. And then if I look at the fidelity, I can see that at every second cycle, once the parity is restored, the fidelity of this is actually quite high. And this is also true for an arbitrary superposition state. So I can actually put an arbitrary superposition state, and my tensor network actually allows me to analyze the density matrix and calculate all these properties. Okay, so Yeah, so how does the fidelity of this depend on the shape of the atomic frequency comb? You can actually play around with the effective coupling strength. So this roof on top, it's like how each part of this comb or how each spins here actually couple with the cavity. And I can play around with what this coupling strength is. I can change this thing. And when I change this, I can see that there is a optimal value of the coupling distribution that gives me the best fidelity in the system. Okay, so this is basically what I'm doing. I'm playing around with the different coupling strengths in the thing. And there is an optimal value for which even up to as far as the fourth revival, so the light can revive 4 times and I still retain fairly very, very high. So this is 0.9 and 1. So I can actually get back the state with a quite high fidelity. So why does this happen? So we can do a quick analysis of the first and the second excitation manifold. And if you look at the energy spacing in the first and the second excited manifolds, you can see that there are certain optimal coupling distributions for which the spacing between the energy levels become closer to each other. So they tend to behave more like harmonic systems. So as they tend to become more harmonic, they tend to interfere and recouple the information way, way better than in the other cases. So you can see like all the standard, so this is the standard deviation, and the standard deviation actually decreases. And for the energy spacing in the second and the first manifold, they all start bunching towards the same point when this gamma by 2 pi is actually 0.19 here, which corresponds to the maximum fidelity that you get in the output. Okay, so with this, I'll end this part of the talk. You can see, so what we were trying to look at is, can you have arbitrary states that can go into a spin ensemble, and can you do a quantum analysis of the entire thing? And that's what we try to show, that you can do a quantum analysis of the entire thing. You can calculate the fidelity of the quantum information that was going in. You can plot what the optical states look like and track them and study them. So in the last part, what we look at a slightly different question. So in general, all these spin ensembles, at least most of them, rare earth spin ensembles, NV centers, they have something known as inhomogeneity in them, which are intrinsic, and it's called inhomogeneous broadening. And inhomogeneous broadenings typically tend to introduce additional losses in the system. And in some cases, these losses could actually be way stronger than the intrinsic losses that are there in the system, right? So why does this arise? This simply arises because all the spins are not identical, and then they don't cohere, rephase, or interfere with the light in an identical manner. So what does inhomogeneous broadening do? It introduces a decoherence in the system. And the simple way to look at it is, if this gamma here, capital gamma here, is the overall line width of the system, and let me ignore the other losses and just look at the cavity loss here, you can see if rho here is the density of states of the inhomogeneously broadened distribution of spins, this actually adds an additional term to the overall line width. And in some cases, even if your kappa is very, very good, so you've really constructed a beautiful cavity with a very high quality factor, even then the inhomogeneity can actually strongly contribute to the losses in the system. So what are the ways in which you can actually get rid of inhomogeneous broadening? So some methods are simple. You can see if you look at the density of state, it says what is the density of states as omega s plus minus capital omega. So capital omega is the effective coupling. So it says what is the density of states at the polaritonic peaks out here. So if you can actually increase the coupling strength omega and push the polaritonic peaks outside, if you can push them outside, in some sense, you would have reduced the effect of the losses due to the inhomogeneity. So this is the density of states at the polaritonic peaks. You move the polaritonic peaks outside where the density of states is actually very, very low. So the second term actually becomes way, way smaller, right? Another thing is a bit more dramatic. You can do something known as spectral hole burning. So you can take two lasers and burn two holes. So you basically detune all the spins that are lying close to the polaritonic peak so that they don't actually talk to the light anymore. And if you burn these two holes here, you can again, of course, see a dramatic improvement in the overall losses of the system. But there's a catch to this. Say for the first case, you can't increase the effective interactions beyond a point. Okay, you've made your cavity as fine as possible. You stacked in a lot of two-level systems within a space to get a high coupling, but beyond a point, you can't really stack any more spins there. So for example, in envy-centered experiments, they tried increasing the density, but then at some point, you have to increase the density so much that particle interactions come into the picture. So you'll see that there's a restriction as to how much capital omega or effective coupling that you can increase. The second part is even more dramatic because as soon as it's burning holes, you have additional lasers that are acting with your spin ensemble, and they can actually create other kind of interactions in the system. So our idea was based on some earlier work on cavity QED. Based on earlier work for circuit QED done by people like Ash Clerk and Franco Nori and others. We wanted to drive the entire system with some parametric two-photon driving. So I have the usual Hamiltonian here, and I add an additional two-photon drive to the system. Now in the squeezed frame, if you look at the effective Hamiltonian, you see that there's this additional exponential to the R that comes, right? So you have the GK, which is your usual spin and light matter coupling, but you have an additional exponential term that comes. And this exponential term effectively increases the coupling that you can have between your system, right? So if I ignore this part, if R is substantially large, I get an effective decay model. And if I can work close to the rotating wave approximation, I'll more or less get back a similar system, but now with a slightly or highly enhanced coupling strength. And you can see this already has some effects. Let me consider just the semi-classical dynamics, not looking at quantum information. I just want to see how the photon number behaves. You can see that if the Rabi oscillations actually drop quite quickly due to the inhomogeneous broadening, so it's coming down very, very sharply. If I introduce this parametric driving, I can restore some of the Rabi oscillations back to the original level. So here I'm not considering any losses. I'm only considering inhomogeneous broadening. So this actually becomes perfect because there are no other losses in the system, right? So by increasing the squeezing parameter R, I can effectively have some kind of a cavity protection effect in the system. Yeah? Okay, so like from GK, I'm going to GK e to the power R. So, but what about quantum information? So fine, you asked me in the semi-classical limit, I just looked at the photon number, and the photon number oscillations were good, and I could increase R and get it back to the normal level. But what if I encode a quantum state in it, and I want to look at the dynamics of the quantum state? Again, let's look at the quantum dynamics for around 100 to 200 spins. And again, we use the variational renormalization method to analyze the system. So we can now do a quick back of the envelope calculations for what the effective line width would be. So this is very similar to what I showed you earlier, but now I've added additional loss terms for the spins in the ensemble. And then this is the expression for the density of states at the polaritonic peaks omega tilde. So tilde here reflects that now we are working in the squeezed basis and not in the original basis. So the tilde comes from that. And I can actually just write down this parameter xi out here, which tries to capture how much of this non-intrinsic losses can I curb in the system. So the system has some intrinsic line width. What I want to do is any additional losses that are coming because of the inhomogeneous broadening, I want to push that to 0 as far as possible. That's what I'm trying to do. And okay, so this is what we get after solving for this 100 spins. So you can see I've taken two distributions which are fairly bad. So if you look at experimental papers, you'll see that, okay, this kind of inhomogeneous broadening is already quite big in some sense. So if I look at a broadening where the width of the Gaussian distribution is 0.7 times the actual effective coupling of the system, you can see that for R equal to 1 by 3/8, I can reduce this gamma n to this semi-classical limit. So this semi-classical limit is the ideal limit where this coupling tends to infinity. So if the coupling tends to infinity, you're just left with what your actual losses in the system are and not the additional inhomogeneous broadening losses. And this yellow region out here is basically the kind of parametric drive that has already been demonstrated in the experiments in the labs using superconducting circuits and trapped ions for these kind of enhancements. So within this operational parameter regime, you can see that we can already reduce most of the extra losses that were coming into the system. But if I'm adventurous and I choose a far higher number, say width of the Gaussian distribution, which is 1.5 times the effective coupling, in that case, I would need to go to higher values of R to actually reduce the amount of losses. So R 1.73 is as high as, I think, stable squeezing that has been demonstrated experimentally across anywhere. And you can see that close to that, you already can reduce quite a bit of the losses in the system. You're not there ideally. If you're working with artificial circuits and superconducting circuits, maybe you can achieve much higher Rs and you can reduce it to way lower values, right? So you can see that the line width can actually be played around with and you can reduce it. We can look at the fidelity and the Wigner function of the encoded state. So if this is the Wigner function of the initial state that I put in, say for a width of 0.753, you can see that at the first revival, this state is completely disappeared. So there is no information about the state anymore because of the high losses that the inhomogeneity is introducing. But if I can have the parametric drive in place, you can see quite a bit of the original information is still revived and kept in the system, right? It will not be perfect because there are other losses in the system too, but you can see the Wigner function. So here you can look at the fidelity of any of this particular initial state. So this is in purple out here for R equal to 1.75. And you can see that the fidelity is actually quite high. We've actually, you don't need to work with this particular state. This shaded line here is for all possible Haar random, around 500 or 1,000 Haar random states of similar kind, and they all fall within a band there, right? That shows that, okay, even if you have inhomogeneity, you have a method by which you can study these inhomogeneous systems, and you can engineer methods by which you can get your information back in the system. Okay, so with that, I'll conclude. Yeah, so I just was a theoretical study of collective states and hybrid architectures. They offer a rich playground. There are a lot of interesting things that you can look at here. You can look at information storage, you can look at protection, you can look at quantum communication, sensing in continuous variable systems. And another interesting thing that we've started working on, and I think Harsh gave a talk on this last week, and that was on how you can design error correction in these collective states. Okay, with that, let me go to the acknowledgements. So the experiment was mainly done in the group of Johannes Fink in IST with Elena, who read the experiments, and Stefan and Matthias. We've been working on the theoretical aspects of this for quite some time. From IIT Bombay, most of the theoretical and the computational work was done by Siddharth Tiwari and Harsh, who's in the audience, and other students, Rahul Shudipto and Harsh. I think even Shudipto is giving a talk later in the conference. And yeah, all of us, we work on some theoretical quantum information in collective systems. Yeah, with that, thank you.
Questions? Can someone pass the mic? Yeah, I can pass the mic.
Am I audible? Yes, thanks for the talk. So I had a question regarding this simulation part of basically this Davis coming type of models.
Yeah.
So how do you typically handle this field modes truncation? Basically, you need to truncate.
Yes, yes, true. So, okay. So it depends upon, so there are many ways in which you can do it. So in some of these methods, it was pretty straightforward. Like we were working with, the average photon number was pretty low. So we could just truncate it to some number, and you actually, along with your, when you track the bond dimension or something for effective losses due to the tensor network, you also have to have a quantity that tracks what kind of losses you're getting due to the cavity. So you can dynamically keep updating that. Another way is if you're actually working with something that has a fixed distribution, you can actually move the entire fog state basis somewhere else and only work along those fog states that give you those distribution and keep track of how it's spreading. So you can try to dynamically update that.
Okay, thank you. And just one more question. Does it also depend on the coupling strength between atom and field modes?
You can actually, so the thing is, I actually have a couple of slides which says why tensor networks work and why they don't. So in closed systems, it's very easy to understand the connection between entanglement and tensor networks, right? You can keep track of how entanglement is growing. But in open systems, when you go to the Lindblad picture, you really don't have an equivalent quantity that can easily quantify something for you. So you can call it total correlations or the Schmidt rank of uh, the Schmidt decomposition you write in the Liouvillean superoperator space, which is some matrix quantum mathematical object rather than a physical object. But yeah, we don't have any underlying theory that would say that why that should increase or decrease, like the area law or something. So in our case, what you do is you take the system up, you write down the matrices, keep track of all the Schmidt rank or the singular values that you have, and you can tweak the code according to what you need. Yeah, but it's true. So if I think of a block sphere and I say all my system starts with spins facing downwards, I can't really drive the system so that they all move along the equator. That's too much correlations to accommodate. That will not work. But in most of these cases, the field is way smaller than the number of spins that you have. So you're moving very close to the thing.
Okay, thank you.
Hi, sorry, can you hear me?
Yeah.
So Himadri, just a kind of, maybe it's not I'm thinking cat states, GKP, like, is there a route to stabilizing those kinds of states by following this philosophy of yours of like inducing this parametric?
I think in principle it should work.
Okay.
But yeah, so in this simulation, what we're doing is we're writing everything in the fog basis. So if you have any information that's efficiently represented in the fog basis, I think it should work because the superpositions are pretty arbitrary. Yeah.
Tried stabilizing a cat state, let's say just as a kind of sim.
Yeah, so there was cat state, right?
Oh, okay, I missed it. Okay.
Yeah.
Yeah.
There was, so we did a coherent state, an arbitrary superposition, and a cat state.
Okay, I missed the cats. Sorry, yeah.
I just had a simple question. I mean, so like when you talk of this n spins in a cavity, I mean, so like what kind of experimental setup were you thinking of? You said something about this NV centers also. Is that kind of experiment people can do in this?
Yeah. So in NV centers, what people, there are two ways of doing it. And so some of the experiments that were in our mind when we were working at were the very low temperature experiments where you have this NV center diamond and you have a line resonator, superconducting line resonator that's passing through. So this is at very low temperature. But I think nowadays people are also looking at working with NV centers at high temperature. and you have something known as, I think Professor Malmo has been working on that. So you have something known as active optical cooling to reduce some of the thermal excitations in the system. And then you can actually try to do something similar on those.
And then when do you get this non-identical versus identical spins? Like, I mean,
yeah, so, okay, yeah, from a theory perspective, it is, from an experimental perspective, I think if you have, say, ultra-cold atoms in a gas, so those cases they behave like very identical systems. I think NV centers, the inhomogeneity can be controlled, like you have samples which are more homogeneous, and some samples are actually quite inhomogeneous.
okay. I mean, if they're like spatially localized at some points, then they would be
Yes, it depends on how they, so if there is, so in NV centers, you have an external field that's creating the transitions.
Okay.
And that can, so you actually sometimes want to engineer inhomogeneity because it gives you other kind of advantages.
Okay.
So I think multi-mode memory operations and stuff are using inhomogeneity in some sense. In some cases, you want to curb the inhomogeneity because it's a disadvantage for you.
Okay. Okay, so if there are no other questions, let's thank Himadri again.
Yeah.